All right, set 2 of the 2023 Physics CE&M FRQs are, this is set 2. You might have gotten the other set. There's set 1 is a different video. If I make any mistakes, I will put them as comments. I might be a little bit slow. There's a lot of questions going here. There's probably a lot of mistakes that I made, hopefully. I think I have the concepts generally right, but I cannot trust my math skills. They have waned over time in terms of accuracy. Okay. Students perform an experiment to determine the vacuum permittivity of epsilon naught. Sphere A is non-conducting charge plus Q attached to an insulating rod. Sphere B is non-conducting charge plus Q. Sphere B mass on a rests on an insulating platform of negligible mass is attached to a vertical ideal spring. Sphere B has the spring are initially at rest. Sphere A is then brought near sphere B without touching. When the centers of the spheres are separated by the vertical distance h, the spring has been compressed the distance y as shown in the figure. The students measure y for different values of h. On the following represents sphere B. Each force, draw the forces. Okay, so what are we doing? We're doing sphere B. Which one's B? B is the bottom one. Okay, so bottom one's got gravity. And so we have gravity going down. The spring's been compressed, probably because you're squeezing it because of gravity, so the spring is going to push upwards on it. And then you are going to have an electrostatic force. They're going to repel, so that's going to be pulling downward. So the downward is F Coulomb force or electrostatic force. Derive the relationship between Y and H and show that this is true. So basically all the upward forces equal the downward forces. So the Kx should equal mg plus the Coulomb force. So the spring is, let me see, how do we know how much the spring constant is? Ks. Distance y is how much is being compressed in the figure. Y is how much it's compressed. So it's Ks times y is equal to m times g plus the Coulomb force, which is Kq big Q over the distance between the two spheres, which is h. So then you just divide by Ks. You get mg over Ks. Plus, and then instead of k, there's 1 over 4 pi epsilon naught, q big Q over h squared. Okay, so pretty straightforward there. Students plot the data as a function of 1 over h squared. Draw a line for the best fit of this data. Well, a very, very flat line, if any kind of line, but I will. No, maybe that. Fair enough. Calculate the experimental value for that. So we got to look at our formula here. So we're going to have y. There, I'm just going to recopy it down here. This is a lot of scrolling back and forth. You guys probably notice I have to do. Okay, but they gave you the formula, so you didn't have to use your derived one. You know, you just have to use the same one. So we're plotting y. So that's already my y. What is my x variable? Really, just this part is x. So then what you see here is that this guy here is my slope. And look, we actually have a y-intercept. Very rare to have, but we have a y-intercept. This is y equals mx plus b. So the slope's going to be this one. So the slope will equal 1 over 4 pi epsilon naught. Little q over big Q. You can solve for epsilon naught. It's going to equal, let's just call that, well, we'll just call it slope. It'll be 1 over 4 pi times the slope times Q times big Q. Now, what's the slope equal to? The slope is equal to, pick 2 points on this curve that you can easily read. I'll pick this one. That's about halfway. We'll say that's about 25, 0.15. And then just pick something like, I don't know, you could draw that straight. I'll just say we go through the 0.0, comma. Imagine I just drew that line a little further. 0, 0.12. So the slope is going to equal 0.15 minus 0.12 over 25 minus 0. Oops. I get 0.0012. And then we're going to plug it on here to find epsilon naught. So it's 1 divided by 4 divided by pi divided by that slope times the charge, which is 2e minus 6. And then they're just 2 of them, so squared. So I get, oh my gosh, I got a terrible number. 0.15, and this is 25. Let me see. Sorry, I just got, I got a really tiny number. This is kind of a lot of far off. So let me just double check. Maybe my line should have been flatter. Should the slope be smaller? Should be a little bit smaller. So I don't know. I don't know. It depends on how good of a line you draw, but it should be 8.85. I'm off by a factor of like 20 or something like that, right? Yeah, I'm off by a lot. Why am I off by so much? That's gonna bother me. Let's see. Do I have it right? I didn't write the KS. Okay, the KS is there because I divided by the KS. That's why it's. So I had to put KS over here. Okay, that makes more sense. That will just make it smaller. KS is 25. Wait, that can't be right. Sorry, so that's the slope. So you want to interchange epsilon, put over the slope there. Yeah. No, that just made it smaller. I made it worse. Worse. Okay, so I don't know. 1.06 times 10 to the negative 11. Oh, no, never mind. That's pretty close. This is only like off by 10% or something like that. Or 20%. 20%? Ah, good enough. Okay. What's the experimental value of mass sphere? We can look at the y-intercept. So the y-intercept, we said it was about 0.12. And that's equal to mg over ks. So the m is going to be 0.12 ks over g. 0.12 times the spring constant divided by 9.8. I get about 0.306 kilograms. Okay. Students modify the experiment by replacing non-conducting sphere B with conducting sphere C as the same charge, Q, and mass. Sphere A is brought near sphere V. Okay, so now we do conducting. It's almost like the set one, just a little slightly different scenario. Is the vertical distance spring, is it greater than, less than, or equal to y? Well, so what's going to happen is when you have the conducting sphere, okay, so conducting sphere, that means like the positive charge is going to be here, the negative charge is here. Because they are closer to the positive charge, it's going to weaken the electrostatic force, right? Because of the charge separation there. So if it's going to weaken it, then basically the spring is not going to get compressed as much. So what is here? It's Y2. So Y2 is going to be, let's see, original experiments in the modified center spheres at H. They're still a vertical distance, same distance spheres, but the electrostatic force is going to be weaker. So Y2 is going to be less than Y1 because the electrostatic force will be weaker because because more negative charges will be closer to the opposite positive charge sphere than before. Okay. Sphere C is then grounded. Ooh, okay, so all that excess charge is depleted. Well, we even do some negative charges, so now we have a negative charge here. Draw an arrow indicating the direction of the platform move immediately after being grounded. It will then move upward because now the force, instead of it being pushed downward, is going to push upward because then these excess negative charges are going to be here. The platform raised stationary, say it does not move, so it's going to move upward here because you're going to weaken that force there. All right. Ooh, this is a weird picture. This is a cool picture. Two parallel conducting rails are separated by a distance d equals 0.3 meters. A resistor resistance R connects the rails. A conducting bar is placed on the slope section of rail H. Above the horizontal section of the rails, frictional forces and the resistance of bars and the rails are negligible. T equals 0, bar is released from rest. Position slides on the slope section of the rails in the perspective view at T1. The bar reaches X1. Smoothly transitions the horizontal section of the rails and enters uniform magnetic field of B1. Okay. Time T2 enters in a region with no magnetic field. So this is let's see, T1. This is T1, T2, T3, and that T4 reaches X4, and then T4. Okay, cool. The bar position XB is a top view, and then the side views here. Okay, fair enough. That's pretty cool. I like this. This is a pretty decent job laying that out. The following diagram is a verse from the top view. Draw an arrow indicating the net force exerted on the bar times B if the net force is 0. Time TB. What's TB? Oh, right here in this region. Okay, so where the loop is increasing, so there's going to be a force to the left. It's going to be, because it's moving to the right, so it's going to be to the left, slowing down. At TB, the speed is this. Calculate the magnitude and the current in the bar. Okay, so this is, the I is going to be V over R, and the induced voltage is the derivative of the flux. And what is the derivative of the flux? Well, the flux is B times A. The magnetic field is not changing, but the area is changing. And what is dA dt? dA dt, the length is not changing, but the width is changing, which is the velocity. So you get this BLV. So that's the derivation for the BLV kind of formula for that that induced voltage there. Yep. So then you just plug it into here. You get the current is equal to BL velocity. This V is velocity, by the way, over R. So the magnetic field is 0.4. What is the length? This length of that wire is D. I guess D. D is, what is D? D is 0.3 times 2.5 divided by the resistance, 0.2. Okay, so 0.4 times 0.3 times 2.5 divided by 0.2 is 1.5 amps. Calculate the net force. Well, the net force is going to be ILB because you've induced a current now. And that current subject to that magnetic field, so you're going to have this. It's going to be B squared L squared, the velocity over R. Or you could just take that current times L, which is the length of the current. Now, the current would be like kind of going through this wire, so that L is like just D. And that D we said was 0.3 there. 0.3, and the magnetic field was 0.4. So that times 0.3 times 0.4, and I left with 0.18 newtons. Sketch a graph of the speed of the velocity as a function of time. So as a function of time is a constant acceleration when it's going down the ramp, so you should expect it to speed up while it's doing that. So during this region, it's going to have constant, because it's constant acceleration during this time. It's just something inclined plane. It's kind of coming down. Then it hits this region. So right in this region, it's going to have a force that's going to slow it down, basically. It's going to like force it to, to slow down, and it's going to slow down exponentially towards 0. I don't know if we're going to make it, let's not make it go all the way to 0, but we'll have a little bit of a curve there. Then from T2 to T3, it's going to have no force acting on it. And then here, there's no flux change. So there's actually, so it's like in this part, it's parallel to the loop. So none of the magnetic field goes through the loop. So there's no induced current and no force. So it's just going to just move straight at that point. The velocity has no force acting, or the object has no force acting on it. So it's just going to move at constant velocity at that point. The original scenario is repeated, but with a new bar that's the same mass, but with non-negligible resistance. Okay. So the bar now has some resistance. The new bar is released from rest and smoothly transitions. Determine the total resistance of closed circuit. Well, in this circuit, if you add a resistor right here in this loop, they're in series. So you're just going to be doubling the resistance. So they're in series. So you're going to say 0.2 plus 0.2, which is 0.4 ohms. They're in series. In the original scenario, the magnitude of the acceleration of the bar immediately after the bar enters the magnetic field is A original. In the new scenario, the magnitude of the acceleration of the bar is A new, is the acceleration. Well, that has to do with the force, right? So we got to think about the force. Force was ILB. Now, the voltage part is not going to change, but the current is V over R. If I increase the resistance, the current will go down. The current goes down, the force goes down. The force goes down, the acceleration goes down. So that's going to be A new is going to be less than the A original, because you say V is the same. I equals V over R is reduced. So F net equals ILB is reduced. And therefore, F net equals A equals, you know, F net over M is reduced as well. Describe a modification to H, B1, or D that will result in a larger induced current in the new bar immediately after it entered. A larger induced current, right? So the induced current we said was V over R. We had that derivation for it. It's BLV divided by R. So you can make it go faster. So if you want to increase this value, you could increase the velocity. So you could increase H. Increase H would result in a higher velocity. You could also, B, you could increase B. It's very obvious in that one. You just pick one of these. You don't have to say all of these. Or the distance. Oh, yeah, sorry. I'm using L because that was the previous set. They used L, but it's D. You could increase D as well. Right? Any of those would work as an answer. Okay, circuit consists of ideal battery and a switch. Switch initially open. Both capacitors are uncharged. Time t equals 0, switch is closed in position A, right? Do not solve a differential equation that could be used to determine the charge. This is pretty similar to the other set. This is the voltage across the resistor. This is the voltage across the capacitor. And you always start with the loop rule. You say the voltage across the resistor plus the capacitor is epsilon. Voltage across the resistor is I times R plus, and then the Q over C is equal to the voltage. Okay, because that's Q equals CV. And so you want a differential equation in terms of Q, right? So I, how is it related to Q, is dQ dt, because the current is coming in and it's going to be, and it's a positive because positive current would add charge here. So it's increasing charge. So you'd say dQ dt times R plus Q over C is equal to epsilon. And that would be our differential equation for Q. On the axis, sketch the graphs of IR and resistor 1 and the energy stored in capacitor 1 as functions of time until steady state conditions are reached. So current through the resistor. So initially you close it, current will start to flow because initially what happens is there's no charge across here, right? So it's 0. So the voltage across the resistor is the full epsilon initially when it's uncharged. So when you close it, you get a lot of current going through the resistor, and then it will decay to 0. So that is the current there. How about the energy stored? That's 1/2 CV squared. C doesn't change, but the voltage is going to start at 0 and it's going to increase and level off. So when you square it, it's going to do kind of the same thing. Okay? Because eventually it will settle to a voltage, the battery voltage. Immediately after T1, so at T1, the switch is closed to position B. So now we're going to, so we've settled. Once you've waited a long time, you've let it settle. So now this thing's going to have the voltage epsilon across it because there's no current flowing. This voltage drop will be 0. And then now we're going to switch it to B. So immediately the voltages, they don't change immediately, but then you'll have some current that's going to flow from here to here because this guy has no voltage to start with. So immediately after the direction, it's directed in resistor 1, it's directed upwards because charge is flowing from capacitor 1 to capacitor 2. And say charge flows from capacitor 1 to 2 because of the potential difference. There's a potential difference. Okay, determine expression for the total charge on the positive plate capacitor 2 a long time after T1. So you wait a long enough time, there's no more current going to flow through either capacitor. So eventually they'll settle and they'll have the same voltage, whatever that voltage happens to be. Now the charge is also conserved, and each of these has a capacitor C, by the way. So basically, you have two things that are true. You have initially, you have a charge that has to equal how much charge is in each capacitor afterwards. And you also know that you wait a long time, the voltage is the same across them. Okay, so we know that the voltage is Q over C. So that means if they're the same capacitance, then they'll have the same charge. So that means it's going to split evenly, right? So that means Q1 will equal Q2, which will equal 1/2 Q0. Total charge of capacitor 2 is that one. Derive an expression for the total energy dissipated by resistor 1 immediately after time T1 until new steady state conditions have been reached. Express your answer in terms of C, Q0, and fundamental constants. Well, the initial charge on the capacitor is 1/2 C times V squared. But V we can replace with Q0 over C. So you get 1/2 C Q0 squared over C squared. That's 1/2 C Q0 squared. Oh, sorry, Q0 squared over C. So that's the initial energy. Then how much energy do we have at the end? Well, each capacitor then has Q0 over 2, 1/2 Q0 over C plus 1/2 Q0 squared over C, right? Just this expression. So that's going to be 1/4 Q0 squared over C if you add them all up. Because this will be 1/4, that'd be 1/8, 1/8 and 1/8 will make 1/4. And so the change in the energy, how much is lost, is 1/4 Q0 squared over C, the difference between those two values. When switched close to position B, a dielectric material with dielectric K equal 2 is inserted between plates of capacitor 2. Determine the charge on the positive plate of capacitor 2 a long time after the dielectric has been inserted. Well, again, we inserted dielectric, the charge doesn't change, so the total charge should be the same, but the current will not flow, and the voltage will be the same. So we have to think about what capacitor 2 is ultimately going to do. So capacitor 2 has a capacitance C, but remember C is going to equal to capsilon epsilon naught over A over D. So if I double that, it's going to go now to 2C. Okay? Now we still know that the total charge is the same, and we know that the voltage is going to be the same, but now the capacitance are not going to be the same. It's going to be Q1 over C is equal to Q2 over 2C, because we've now doubled their capacitance. So now you know Q1 is equal to 1/2 Q2. And so now we plug that into there, we get 1/2 Q2 plus Q2 is equal to Q0. This is 3/2 Q2. So then Q2 is going to be 2/3 Q0. That's the charge on capacitor 2. With the switch closed in position B, a wire of negligible resistance is connected between the two corners of here. Express your answers to E in terms of RCQ naught. Derive an expression for the current resistor 2 immediately after the wire is connected. So the switch is still closed. We have, what have we done now? We have a VC here. We have a VC. And what we've done is now we have a wire of negligible resistance connecting the two. So you shorted this thing out. Or you connect, oh no, you didn't, you just connected here to here. You didn't short it here. You connected from here to here. Okay, derive an expression for the current R2 immediately after the wire switch. So there's no voltage drop across here. Wait, I'm so confused. Oh, I see. They put the resistor. Was there a resistor 2 to begin with? Did I mess that up? Let's see. This is resistor 1. Oh, I didn't even see this resistor here. Is that going to affect anything? Did I use R anywhere? I didn't use that R for anything. Okay, never mind. Okay, so now what we're doing is we have a voltage across here. That VC, by the way, okay, what is that voltage equal to? It's equal to just Q over C, right? You could say like Q1 over C, which would be Q1 was 1/3 Q0 over C. Okay, so it's 1/3 Q0 over C. That's the voltage across here. And then if you kind of think of it as like, well, I've closed it at this point, and oh, they already have the same charge. So let me see. I guess it's like you could do a loop, right? We could do a loop kind of thing and see like, is there a voltage drop here? So this voltage drop here will have to match this voltage drop. So you would have like VC from here to here. So here, sorry, here to here has to be the sum of these three drops here. Okay, IR, but this is already VC. I don't think there's gonna be any current through here. Am I confused? Let's see, you short this point and this point. No, there's some current flowing. I would probably redraw the circuit just because I'm getting a little confused. So here's VC. This is the capacitor. We have R1, oops, or R, and then we have that capacitor. But we also have R is connected to the other part, another branch that has R2 on this side. So then it's like this is connected not only to here. So these two share a bottom connection, but then there's another connection from here, the top of this resistor, to the bottom of this resistor through here, right? That's what that wire is doing. It's creating this new branch where the bottom is connected to here through this resistor. Right? Are those parallel? Yeah, this guy is parallel with this guy because they're connected here and they're connected here. So this resistor is parallel with that guy. And is it parallel with anything else? No, it's in series. Well, it's not really in series, but like, yeah, it's like, okay, so that's what the circuit should look like. And this is 2C, and then this is C. And now you're looking at what the voltage is. We know this voltage is 1/3 Q0 over C, and this voltage drop here is 1/3 Q0 over C. So right after this is immediately after we've closed it. So right after we close it, what does this resistor 2 sees? He sees this voltage drop right here, 1/3 Q0 over C. So the I through 2 is going to be the voltage of 2 over R2, which is just 1/3 Q0 over C divided by R. Okay. Determine now if you wait a long enough time, there's no current that flows into here. So there's no current through here. There's no current through here. So there's no like if there's current through here, where's it going to go? It's not going to go anywhere. So then the current's going to be 0. So to determine the current, it's going to be I is equal to 0. There's nowhere for the current to go at that point. And that's the end.